Hi, in this lesson I am discussing Edexcel IAL Unit 6 past paper, May-June 2021. Okay, this is the first question. Diagram is given like this. So this question based on electromagnetic induction. The wheel, there's a small strong magnet is attached to the wheel and wheel is rotating. So you know when the wheel rotates, the magnet when it passes closer to the or when it passes across the coil, there will be rate of change of flux linkage and voltage will be induced. And the coil is connected to CRO, so whenever voltage is induced, there will be pulse formed on the CRO screen. Okay, on CRO screen, you know, always x-axis, you know, on a CRO screen, it's like a graph paper. X-axis is always time and the y-axis is always voltage. You can change the divisions of the x-axis or you can scale the x-axis by using time knob. For example, if you keep the time knob at 2 milliseconds, that means each division on the x-axis is equal to 2 milliseconds. Y-axis is always voltage, that is the scale could be adjusted by using voltage knob. Okay, so here the graph is given like this, and the first part is as the wheel rotates, a series of pulses is displayed as shown. Describe how a value of the time period should be determined from these pulses. So they want to find the time period of rotation of the wheel. You know, when the wheel rotates, when the wheel passes closer or when it passes across or passes across the coil, voltage is developed or voltage is induced. So the time period between the two adjacent pulses is the time period of rotation of the wheel. Okay, that's the idea. When it passes, when it just passes by the coil, there will be rate of change of flux linkage. So a voltage peak is formed on the screen. So the time period between adjacent pulse is the time period of rotation of circular motion of the wheel. So how can we, the question is describe how a value of the time period should be determined from these pulses. So here it's better to find the one division. So you know one division marked on the given diagram. So count the number of divisions between first and the last or first and the third. That is easy because here between first and the second you can see the divisions are slightly away from the second pulse, but first and the third they are on a division vertical line, they are falling on it. So count the number of divisions between first and the third. The procedure they ask you, how will you find it? So you can say count the number of divisions between first and the third pulse, multiply the number of divisions you counted by, you have to see the time knob where you kept the time knob. So count the number of divisions between first and the third pulse, right? Multiply the number of divisions counted by time per division. So the time per division means that is the value you mark, you kept the time knob. Okay. So for example, if you keep it at 2 milliseconds, count the number of divisions between first and the third part. So the number of divisions between first and the third is 1, 2, 3, 4, 5, 6, 7. So I should multiply 7 into 2 milliseconds if I keep the time knob in 2 millisecond division. So the answer we can write like this. I am not writing it. Simple answer. You can say measure the number of divisions or count the number of divisions between the first and the third pulse. Okay, count the number of divisions between first and the third pulse. Then multiply it by time per division that you can obtain from the time knob adjustment. Okay, so that will give twice the period of rotation of the wheel because time period is this one. This is another time period. So we are measuring from here to here. So divide it by 2. That will give the time period of rotation of the wheel. Okay, for the B part, this data is given. That means you can keep the time division, the time knob, either in 1 millisecond per division or 2 millisecond per division or 5 millisecond per division or 10 millisecond per division. You can adjust it one of the place. They are saying it. So the wheel is rotated. The speed of the magnet is calculated or measured as 22.2 meter per second. The question is, explain which of these scales. So one of the scales you can choose it. Which of the scales, or more than one you can choose it. Which of the scales would display two complete pulses on the screen? You would have done, if you would have done the practical, you can see when you change the time knob, right, the time knob, you can see the size, the gap between the pulses will change on the screen. If you have done the practical, you will see that. So here the diameter of the wheel is also given. So we want to see only two pulses, right? In the diagram, they gave three pulses, but we want to see only the two pulses. So if we want to see only the two pulses and the speed of rotation is 22.2 meter per second, which time division should be adjusted for the time knob? Okay, so we'll find the time period. So we know that B is equal to R omega, omega equal to 2 pi over T, omega, and we know that omega equal 2 pi over T, right? So speed is given 22.2, equal R is given 25.4 centimeter is the diameter, convert to meter, divide by 2 to get it radius. In omega, 2 pi over T, find the T, you will get 35, 0.0359 seconds. So this is in milliseconds. So I'll convert to millisecond. That will be 35.9 milliseconds. So the interval between, on the screen, the time interval between the two adjacent pulses must be 35.9 millisecond. I should get 35.9 millisecond between the two pulses. But at the same time, I should see only two pulses, not more than two. And also they are saying we should see two full pulses. So we can't have a pulse something like half of it or something like half of it like this. We can't see. We have to see the full pulses, right? Okay, so what's the procedure we can see? You can count it on the given graph on page 2. There are, we can, if you want to show complete two pulses, the possible x divisions will be 8, right? The possible x divisions will be 8. Okay, so if you want to have two complete pulses, the gap between the two complete pulses should be 8 divisions. So 35.9 milliseconds means one division should be, so one division should be how much? 35.9 divided by 8. So one division should represent 4.48 millisecond per division. So approximate, I can say 5 millisecond per division. So that's the suitable adjustment. 5 millisecond per division is a suitable one. If you adjust it 1 millisecond per division, you won't be able to see two pulses because the time is too small. So 1 millisecond, if you adjust it, there is no enough space to show the time interval of 35.9 millisecond between the two adjacent pulses. If you adjust it at 10 millisecond also, what will happen? You can see, but the problem is you will see more than two pulses, right? Yeah. So the suitable is 5 millisecond per division. Okay, question number 2 about the practical related to latent heat of vaporization. A diagram is given. First part, devise a plan to determine the value of L using a graphical method. You should include a circuit diagram and any additional apparatus required. So A part, we need to draw a circuit diagram. Question number 2. So you know the circuit diagram. So the heater, you can draw the heater or you can put a heater just like this. This is the power supply. You can DC power supply. You need an ammeter to measure the current flow. This is the heater. There should be a variable resistor to adjust the voltmeter ammeter to keep voltmeter ammeter reading constant. So here is the beaker. Voltmeter should be connected across the heater. So this is the heater. So this circuit diagram is enough. Okay, that's the second part. They ask to draw the circuit diagram, and then we need to explain the procedure. So you can say first fill the beaker is given as a heat-proof beaker. So fill the beaker with water, switch on the circuit, let the water to boil. So we should wait until the water start to boil, right? So when or you can pour boiling water. Either way you can start, but better you can see how do you know the water is boiling. You can see the bubbles are formed. So switch on the circuit, let the water to boil. When the water boils, record the weighing scale or balance reading and switch on a stopwatch. At proper time intervals, you can take 2 minutes or something like that. At proper time interval, record the weighing scale reading. So you are going to tabulate the readings at 2 minutes. This is the mass. At 4 minutes, this is the mass. Like that, you are going to record the reading of the time and the reading of the weighing scale or the balance. Right. Then what we are going to do after taking maybe 10 or 15 readings, we need to calculate the amount of mass vaporized. So we know the initial mass when we start the practical. When the water start to boil, we record the mass. If I say that is the mass m naught, the initial mass is m naught, the amount of mass display or vaporized is m naught minus m at a particular time. That is the amount of mass vaporized during that time. And throughout the practical, we should maintain the voltmeter ammeter reading constant, because then only the power of the heater will remain constant. So we know the equation, the power is equal to, we know P equal VI, so VI, and P is equal to delta M, sorry, P into T will be equal, that's energy given, P into time, that is equal to delta M into latent heat of vaporization, right? So we are going to rearrange it in order to plot a graph. So we know that time is the independent variable, delta M is the dependent variable. So delta M is equal to P over LV into T. We can plot a graph of delta M against, this is radian, delta against time. You will get a straight line through the origin. From the graph, find the gradient. So from the graph, find the gradient. So gradient will be equal to, I use M for gradient, not mass. This is gradient equal P over LV. So you know the power, you know the voltmeter ammeter reading. So you know the power of the heater. So LV is equal to P over M. So from this, we can find the latent heat of vaporization of the water. Okay, so question number 2B part. One significant source of error in this experiment is the uncertainty in the mass reading due to the water moving as it boils. So sometimes they can condense on the beaker. So that can cause uncertainty, that can cause error, even systematic error can be caused. Explain how another significant source of error affects the value of LV. Okay, so here in the diagram they showed, they said heat proof beaker, but upper part open is there. There is opening on the top. Because we can't close it, we can't use a lid, then the water will condense there. So to avoid that, it should be open. So if it condenses, it can, again, the water droplets can fall into the beaker. So that will certainly give a big error in the experiment. To avoid it, the beaker is kept open. So if the beaker is kept open, heat will be lost to the surrounding through the opening of the beaker. So that will be another possibility of having uncertainty or error. Actually, not an uncertainty, it's an error, systematic error in the experiment. So the question is, explain how another significant source of error affects the value of L. Explain. So there we can say there will be heat loss to surrounding. So that means you are supplying heat from the heater, and you say the heat you supply is power into time is the heat you supplied, and you, when you are calculating it, you say that all the power is transferred to the water. We assume like that, is it? So delta P into T is equal to delta F, the mass vaporized, into LV, and we plot a graph of power against, sorry, we plot a graph of delta M against T. So you will get a graph something like this, straight line through the origin, right? So that means at a particular time, you are getting the mass vaporized is this much. But if there is no heat loss to surrounding, if all the heat supplied by the heater is used to vaporize, at a particular time, the mass vaporized will be more. Is it? So at that time, the mass vaporized will be more, means you will get a graph something like this with a larger gradient. You will get a graph with a larger gradient. Because if there is no heat loss to surrounding, at a particular time, the heat supply will be more, so more mass is vaporized. So you will get a graph something like that. So your graph, due to this problem, due to the heat loss to surrounding, your graph will have lower gradient than the actual gradient. Is it? So we found, we rearranged it in the previous part. I plot a graph of delta M equal P over LV into T, and I said this is the gradient. This is the gradient. So I got a lower gradient than the actual gradient. I found the LV by using LV equal or M equal P over LV, and I found LV equal P over M. I am getting a lower gradient than the actual gradient. So my experimental value of LV will be greater than the actual LV. LV means latent heat of vaporization. So practically, I will get a value of LV which is greater than actual value. That's the explanation you should give. So here the question is 3 marks. Explain how another significant source of error affects the value of LV. So you can say there will be heat loss to surrounding through the opening part, the upper part, opening part of the beaker. So the amount of mass vaporized will be lower than the actual mass vaporized. So the graph will have a lower gradient than the actual gradient. Therefore, the value obtained through the experiment, the value of latent heat of vaporization obtained through this experiment will have a smaller value than, will have a greater value than the actual value. Again, I'll tell the answer. Due to the opening of the beaker, heat will be lost to surrounding. Therefore, the mass vaporized will be lower than the actual amount of mass should vaporize. Therefore, the gradient of the graph, what I obtained, will be lower than the actual gradient. Therefore, the value obtained from the graph, the latent heat of vaporization value obtained from the graph will have a greater value than the actual value. That's the answer you should write. Okay, question number 3. This is something related to simple harmonic motion oscillation of a trolley, which it is connected to two springs. The student used a stopwatch to time the oscillation. Describe how he should modify the equipment to make this measurement as accurate as possible. So whenever you are measuring time period of oscillation, whether it is a simple pendulum or spring mass system in vertical oscillation, or even a oscillation, something like that, you need a pointer, or you need a marker to calculate the number of oscillations. So you can have like this. When the trolley is at rest, you can have at the center part, because during the oscillation, it should always pass the point where you are keeping a pointer to count the number of oscillations. So when the trolley is at rest, you can mark almost at eye level center of the trolley, you can mark a line or you can keep a pointer on the table, on the bench, and you can have a line or you can mark a line on the trolley also eye level. So whenever it oscillates, whenever this line passes this pointer, you can count the number of oscillations. Simple method, right? Don't keep anything somewhere here or anything, because sometimes it might pass through that point initially, but due to damping, it might not reach the point. So always, whether it's a simple pendulum or uh, spring mass oscillation in vertical plane, whatever the oscillation, keep the pointer at the equilibrium position, because always it will pass through it, even there is a damping. So you can say the answer, you can say keep a marker or pointer on the bench at the equilibrium position when the trolley is not oscillating. Keep a marker or keep a pointer at the equilibrium position when the trolley is not oscillating. Keep a line on the mark on the trolley at the same position. So that will be used to count the number of oscillations. That's the answer you have to give for A part, first part. A part, second part, describe two techniques he should use to reduce the uncertainty in the value of the time period. So you can say measure the time not for one oscillation, measure the time for larger number of oscillations. Normally we do for 10 oscillations, not less than 10, 10 or 15, sometimes 15 it might stop. So better you can say large oscillation. So first you can say measure the total time for larger number of oscillations, say example 15 oscillations, and divide the time measurement by 15. Repeat the experiment 5 times and find the mean value. That's the answer you should say, right? So that we normally do during all experiments where we are measuring the time period of oscillation. Measure the time, total time for 15 oscillations, divide it by 15 and get the time period of one oscillation. Repeat this experiment and find the mean value of time period. Okay. Okay, the same question, third question, B part, something related to graph. I can't draw the graph on the board, but most of the students have no problem plotting a graph or scaling the graphs. The B part says the student added masses to the trolley. He measured the total mass, capital M, of the trolley and mass. He recorded the following values. So they are giving how he is changing the mass by adding masses and the time period. Okay, so plot a graph of logarithmic scale, log t against log m on the grid. So you need to find the log m and log t. You can find it in 2 decimal point or 3 decimal point. Either one, they accept it, right? But don't find it in 1 decimal point, 1 SF. You can find it in 2 SF or 3 SF, both m and t. So after, when you are scaling the graphs, normally try to scale like we don't use any divisions in the order of like 3, 6, 9. We don't use, or 0 0.3, 0 0.6, 0 0.9. In the order of 3 we don't use. Same way we don't use in the order of 7, 14, 21, or 0 0.7, 0 0.14. That way also we don't use. Normally we use like 1 into 10 to the power plus or minus 1. That means 1 into 10 to the power plus or minus n means something like we can scale it 0 0.1, 0 0.2 like that, or 0 0.01, 0 0.02, 0 0.03 like that, or 1, 2, 3 like that, or 10, 20, 30, or like 100, 200 like that format we use. Also, we use normally 2 into 10 to the power plus or minus n. That means like 0 0.2, 0 0.4, 0 0.6, or 0 0.02, 0 0.04, 0 0.06, like those formats, or 2, 4, 6, 8, those formats normally we can scale it. The next scale normally we use is 5 into 10 to the power plus or minus n. That means 0 0.5, 0, sorry, 1.0, 1.5, that format, or 0 0.05, 0 0.1, that format, or 5, 10, 15. Normally those are the scales we normally draw it on the graph. We don't use 3, 6, 9, or 7, 14, 21. Those type of scales we normally don't use. Remember that. And also try to scale such that you are using at least more than 50% of the sheet given, something like 60% or something like that. So according to that, little bit of trial and error, you have to scale the graph paper, the grade. Okay, the same question, question number 3, part B, second part. The student predicts that the relationship between T and M is given by T equal 2 pi square root of M over K. That equation is given. And you are plotting a graph of log T against log M. That's the way you, the data given, and you are plotting the graph. Where K is a spring constant. Discuss the validity of this prediction. So you plot a graph. So when you plot a graph, you will get a straight line, right? So from that graph, you are going to find the gradient. So the idea here, they are giving an equation, something like that. That type of equation, mostly your paper, the graph is related to logarithmic scales, right? Log graphs you normally draw. So they ask you to check whether the equation, the prediction is valid according to the practical data you obtain from the graph. Okay, so if it is correct, now you plot a log t against log m. We will take log for this equation. So that means log t is equal to, when you take logarithmic, log 2 pi plus half log, uh, I can say log 2 pi into, okay, I'll step by step, I write log m over k to the power of half, is it? So I can write this, rearrange it, that log t equal, half comes here, half log m plus log 2 pi over square root of k. That's the way you are going to get it. So you are plotting a graph of log t against log m. So this is going to be the y-axis. This is going to be the x-axis, means this should be the gradient. This is the y-intercept point. You are going to get it something like this. Okay, so when we, from the given equation, when I take log, why I took log? Because you are plotting a graph of log t against log m. So from the theoretical equation, I took log on both sides and I got an equation like this. Okay, this equation also straight line. You already plot a graph which the data collected through practical, right? So if the practical is tallying with the theory, then you find the gradient from your graph. That gradient should tally with this value. So find the gradient of your graph. You will get, after you plot the graph, you will get gradient which is almost 0.51 or 0.52. Here also the gradient is half, which is 0.5, is it? So that means practically you are getting a gradient of 0.5. Theoretically also the gradient should be 0.5. So that means you can conclude, yes, the equation is valid, or that is an acceptable equation, because practically the results what you got is a straight line. Its gradient, you find it, that also same as this value 0.5. Okay, so there you can conclude. After this you have to write this one, you have to derive this format, then you should say you have to find the gradient from your graph. Okay, you have to find the gradient. Okay, then compare your gradient what you obtain from the graph with this value. You will get almost the same, 0.51, 0.52 you are getting it when you plot the graph. So there you can say this equation is correct and tallied with the experimental results. Okay, so the third part, determine the value of k. Okay, so if you properly scale the graph, you will get y-intercept point. So you know what is the meaning of y-intercept point? The value of y, where the graph cuts the y-axis when x equals 0. So you will get a proper y-intercept point if you scale it properly. So you will get the y-intercept point almost minus 0.06 or 0.58, something like that. You will get it, right? So if you know, if you can get the value of y-intercept point from the graph, theoretically the y-intercept point is this one. So if you, for example, if you are getting the y-intercept point minus 0. 0.06. That should be equal to log 2 pi over k. So take both sides and the log, right? And solve it and find the value of k. You will get almost 52 odd, 52.1 or something like that. You will get the value for k. So in case if you are unable to get y-intercept point on your graph. So from your graph, take a clear point. So from your graph, take a clear point on your line, take a clear point. From that, find the y value and x value. So the y value will be log t and x value will be log m. From your graph, take the values of log t and log m by choosing a clear point on a line, on the best fit line. Okay, don't take the readings. You should take it from the point on a line, on the line, right? So you know the log t and log m values. Substitute those values in this equation. In this equation, you can substitute the log t and log m. You got it from the graph. So solve it. You will get the k. In case if you are unable to get the intersect point, you have to do that way. Okay, question number 4, that is related to error calculation uncertainties. Okay, a student measured some dimensions of thick circular lens. The diagram shows approximate values. So they are saying the thickness of the edge of the lens is 2 millimeter. The thickness of the center part of the lens is 1 centimeter. The diameter of the circular part of the disc is 5 centimeter. So two diagram photographs are given for vernier caliper and micrometer screw gauge. The question is, first part, A part, first part, question number 4. I'm discussing now question number 4, the error calculation part. Uh, State with a reason which of these measuring instruments, so they are giving vernier caliper and micrometer screw gauge, which of these measuring instruments she should use to measure the D. So you know the D is almost 5 centimeters. So actually, range of the micrometer is too small. You know that. So better the suitable instrument is vernier caliper here, because range of the this micrometer screw gauge, the length is not enough to measure 5 centimeter. So the suitable instrument is vernier caliper. That's nothing, just normal question. Okay, if you have done the practical, you know that. Okay, now second part, A part, second part. The student recorded the following values of D. The D means the diameter of the circular part of the lens, measured at different points across the lens. So 5.10, 5.11, 5.10 centimeters are given. She concluded that because her measurements were precise, they must be accurate. So precise means when you are taking repeated measurements, if the readings are very closer to each other, we call they are precise measurements or precise readings. But precise readings, we can't 100% sure. We can't conclude that I got precise readings, therefore my readings are accurate. No, accurate means much closer to the actual value, right? Precise means repeated measurements are very closer to each other. If you get such that type of readings, we can say my measurements are precise. But you can't say they are accurate. Accurate means the mean value should be closer, or these values should be closer to the actual value. So here the question is, explain why this conclusion may not be justified. So the student is saying she concluded that because her measurements were precise, she is getting 5.10, 5.11, 5.10. So they are precise. They are very closer to each other, repeated measurements. So they must be accurate, she is saying. The question is, explain why this conclusion may not be justified. Okay. The reason is the measuring instrument might have zero error. So if the measuring instrument, the vernier caliper has zero error, yeah, you are getting precise readings. That means they are the same, but they will have zero error. All readings have zero error, means they will not be equal to actual value. That means they are not accurate. So the simple 2 marks, you can say there could be zero error that will cause systematic error, Therefore, even the measurements are precise, they will not be accurate or they will not be closer to actual value. That's the answer you should give. Okay, so now we'll go to the calculation part, error calculation, interesting parts. Right, okay, so B part of the question number 4. Okay, so the student measured the thickness X. Thickness X means you can see the diagram, that is the thickness of the edge of the lens using micrometer screw gauge, and there are 5 repeated measurements are given: 2.11, 2.10, 2.13, 2.14 and 2.11 millimeters. Calculate the mean value of X in millimeter and its uncertainty. Okay, so before watching these error calculations, I uploaded a separate video for error calculation. So the link will be given here in this description of this video also given. So I taught how to calculate the uh, mean value, how to calculate the uncertainty, percentage uncertainty when there is repeated measurement. So I'm going to use that now. So the B part, question number 4, B part. So mean value of X, so add all those given values and divide by 5. 2.11 plus 2.10 plus 2.13 plus 2.14 plus 2.11 divided by 5. So you will get 2.12. You should give it with the same decimal point. So 2.12 millimeter. Uncertainty in X. You know, repeated measurements, half, max minus minimum. So maximum is 2.14, minimum 2.10. So that will be 0.02 millimeter. So I can say X equal 2.12 millimeter plus or minus 0.02 millimeter. Okay, so C part. This is the refractive index of a lens is given by 1 plus d squared plus t minus x all things squared over 8f into t minus x. So here t is the thickness of the lens that's given on the diagram, thickness of the lens at the center part of it. X is the thickness at the edge. F is the focal length. Okay, very complicated equation, but we can handle it. So these are the data given. This one we calculated in the previous part. We need this value also in these error calculations. So that's the reason I wrote it with different color, red color. This is not given. We calculated. This one we calculated in the previous part. That is, we calculated on part B, right? So I wrote it here. Easy for me to use that also. The question is, C part first part, question number 4, C part first part. Determine a value of n's. Normally we give it in 3SF. Just substitute the values. You will get the n. So I'll do the C part first part here. N is equal to 1 plus. Substitute the values in this equation. So 5.10 we'll give it in centimeter. All summer, this is given in millimeter. Careful, this is also in millimeter. We need to convert to centimeter when we substitute. So d squared 5.10 squared plus we need to find the t minus x. T is given in millimeter, convert to meter, 0.830 minus x is in millimeter, 0.212 all things squared divided by 8 into focal length is 9.8 centimeter into again 0.830 minus 0.212. Solve it. You will get 1.54. That's the refractive index. We'll calculate it from this equation. Okay, the second part, show that the percentage uncertainty, that is the second part of C part, show that the percentage uncertainty in t minus x is approximately 0.5. So t minus x, we need to find the percentage uncertainty in t minus x. Okay, you know the percentage uncertainty of a quantity. See the video I already uploaded regarding error calculation. The link is given in the description part of this video, so you can go through it. So there, you know the percentage uncertainty equal uncertainty over value into 100. So here we need to find the value of t minus x. So we'll find the value of t minus x. So t minus x is equal to t is equal to 8.3 millimeter. So I can keep it in millimeter here. 8.30 minus x is 2.12 in millimeter. So that will be 6.18 millimeter. So I need to find the percentage uncertainty in t minus. So uncertainty in t minus x. So yes, in my that lesson, I told that when you are adding or subtracting measured quantities, you need to add the uncertainty. So here we are subtracting x from t, but uncertainty of t minus x means uncertainty of t plus uncertainty of x. Uncertainty of t here 0.01 plus uncertainty of x 0.02. So that will be 0.03 millimeter. Okay, so I need to find the percentage uncertainty. That's the question. Percentage uncertainty in t minus x. That will be equal to uncertainty t minus x. That is 0.03 divided by value of t minus x. That is 6.18. Both are in millimeters into 100%. So that you will get 0.49 percentage. Approximately 0.5 percentage. Okay, so third part, C part. So the question is, show that the percentage uncertainty d squared plus t minus x all things squared, that is almost equal to, we had to show that that is almost equal to 0.11 centimeter square. We need to show that. This red color what I wrote, we had to show the percentage uncertainty of this quantity is equal to 0.11 centimeter squared. Okay, so not percentage uncertainty, they asked to find the uncertainty, not percentage uncertainty. Uncertainty in d squared plus t minus x all things squared equal to 0.11. We had to show that. Okay, so here you can see that d squared is added with t minus x all things squared. So there's a plus sign. We know that when quantities are added, uncertainty will be added. So that means there are two methods we can do this one. So first method, so here what I'm going to do, I'm going to find the uncertainty in d squared, then uncertainty in t minus x all things squared. If I find, then I should add those two uncertainties to get the uncertainty of the whole thing. Understand? Because there's a plus sign. So we need to first find the uncertainty in d squared. I know the d. So uncertainty of d I know 0.01 centimeter. I need to find the uncertainty d squared. Okay, how can I find it? Okay, I'll start like this. So I can say first I need to find the uncertainty in d squared if I want to find. First, I should find the percentage uncertainty in d squared, is it? I need to find the percentage uncertainty in d squared. Then I should find the value of d squared. Then I can find the uncertainty in d squared. Lot of work there, we'll see that. Okay, so first I should find the percentage uncertainty in d squared, that is equal to 2 times percentage uncertainty in d. So I told that whenever there's an index, it comes front, right? See the lesson that I did already. So percentage uncertainty d squared equal to 2 times percentage uncertainty d. So 2 times percentage uncertainty d means I know the uncertainty d 0.01. So 0.01 over d, that is 5.10 into 100%. So that will be, that's a percentage uncertainty in d squared, that will be equal to 0.392 percentage. Okay, so I found the percentage uncertainty in d squared. So how can I find the uncertainty in d squared? I need to find the value of d squared. So I can say uncertainty in d squared equal value of d squared. So d is 5.10. So 5.10 squared, that's the value of d squared, into 0.392 over 100. So that you will get 0.102 centimeter square. So I found the uncertainty in t squared. Okay, now I need to find the uncertainty in t minus x squared. Okay, so to find it, I know the percentage uncertainty of t minus x. We already found it in the previous part, that is part C, second part. We found the percentage uncertainty in t minus x and we got 0.49 percentage. So I need to find the percentage uncertainty in t minus x all in squared. So we can find it like this: percentage uncertainty in t minus x all in squared. Again, there's an index, 2 times percentage uncertainty in t minus x. 2 times percentage uncertainty in t minus x, I found it in the previous part as 0.49 percentage. So that will be 0.98 percentage. Okay, so I need to find the uncertainty in t minus x all things squared. Then only I can add the uncertainty of t minus x squared and the uncertainty of d squared to get the uncertainty of the whole value, right? So uncertainty in t minus x all things squared, how can I find it? Value of t minus x, I need to find it. So that is 0.618, value of t minus x. You can say value of t minus x, t in centimeter, 0.830. X is 2.12. So you can find the value of t minus x. So I can do like this: 0.830 minus 0.212. So that is t minus x all things squared into 0.98 over 100. So there you will get the uncertainty in t minus x all things squared will be 0.004. Okay, so I know the uncertainty in t minus x, I know the uncertainty in d squared. I need to find the uncertainty of this value. How can I find it? Uncertainty of d squared, that is 0.102, plus this one, uncertainty of t minus x all things squared, 0.004. You will get 0.106, approximately 0.6. I can approximate to 11 centimeter squared. Okay, so method 2 for the same question, part C. third part, question number 4. Okay, so I need to find the uncertainty in this one. So I'm going to find the maximum value of this one and the minimum value of this one, then half max minus min. So for simplicity, I'm saying I'm going to define z is equal to d squared plus t minus x all things squared. So that's the equation given. We need to find the uncertainty of this one, means I need to find the uncertainty of z, d squared plus t minus x. That's the given equation. I need to find the uncertainty of that one. So I just let it be z. So what is z max? I need to find the maximum value of z max, means d max, maximum value of d. How can I find the maximum value of d? 5.10 plus 0.01 will give the maximum value of d. So d max squared plus, I need to find the maximum value of this one, means t max. T max is 8.30 millimeter, convert to meter, 0.830 plus 0.01, is it? T max minus, I need to get the maximum value which is inside the bracket, means x will be the minimum. X should be the minimum. Then only I'll get maximum. Say for example, a minus b. If I want to get maximum value of this one, I should get the maximum value of a and the minimum value of b, because I'm subtracting, is it? That's just IGCSE maths. So minimum value of x, x minimum. So how will you find the x minimum? This convert to meter, 0.212 minus 0.002, or you can subtract it and convert to meter. Okay, so that's the x minimum. Okay, we'll substitute. So that will be d max will be 5.10 plus 0.01 all things squared plus t max will be 0.830 plus 0.001, that is t, that is 0.001 when you convert millimeter to meter, minus x minimum. X minimum will be 0.212, x minimum, this one 0.212 minus 0.002 all in squared. So you will get a value of 26.50. Now z minimum, that is I should find the minimum value of the given function or equation, whatever it is. How can I get it? So for that, d minimum squared plus t, I need to get a minimum value, means this is t minimum minus x maximum. Is it? When I subtract larger value from the lowest value, I'll get the lowest value of this one, all in squared. Okay. D minimum, you know that 5.10 minus 0.01. So T minimum, that is 8.30 means 0.830 minimum minus 0.001. X maximum 0.212 plus 0.002. Okay, solve it. You will get the minimum of this function. That will be 26.29. Okay, so I need to find the uncertainty of z. Uncertainty of z means uncertainty of this one. Is it? This I defined as z. So I can say uncertainty in z. Z means d squared plus t minus x. So that is equal to half z max minus z minimum. So half z max is 26.50. Z minimum is 26.29. You will get 0.105. That means 0.116. centimeter square. Okay. Okay, so the last part of question number 4, we got the refractive index already 1.54, but we need to identify whether this material is made of pyrex or crown glass or flint glass. So these are the standard value of their refractive indexes are given. We need to give the final conclusion. I told that in my previous lesson. That is the final part of all the error calculation what we are doing. We should be able to give the conclusion, right? So we are going to find the conclusion whether the refractive index what I use in the laboratory, could it be one of it? Okay, I'm going to identify. Okay, so this also can be done in 3 different methods. The first method is we find the uncertainty in the refractive index. We need to find the uncertainty in the refractive index. Then we will find the range in the refractive index by using the uncertainty. Then we'll check whether any of these values falling within that range. If any of that fall, I can say that is the material this lens made of, right? So I need to find the first uncertainty of refractive index, first method, right? So uncertainty of refractive index, if I want to find, so it's given in a very complicated equation. So I need to find the percentage uncertainty. So how to find the percentage uncertainty? Okay, we'll find the percentage uncertainty first. So that is the equation n equal 1 plus that format. So I can say percentage uncertainty in n, the refractive index equal to. So this is a number, it has no percentage uncertainty. So I need to find the percentage uncertainty in the numerator and the percentage uncertainty in the denominator. You know, this quantity, the whole thing, d squared plus t minus s all. So that is divided by this one. So we know that when two quantities are divided, their percentage uncertainties will be added. So I should say percentage uncertainty n is equal to percentage uncertainty in d squared plus t minus x all things squared, okay, plus percentage uncertainty in 8f t minus x. Okay, so that means I'm finding the person. I'm going to find the percentage uncertainty of numerator and denominator. We know that I told that in my previous lesson. Z equal y over x means z equal y over x means percentage uncertainty in z equal percentage uncertainty in y plus percentage uncertainty in x. So here this whole thing is divided by this one. So number one that has no uncertainty of percentage uncertainty because it's just a numerical value. So percentage uncertainty in n equal percentage uncertainty of this numerical value divided by, plus percentage uncertainty of this one. Okay, right. How can we solve this further? Percentage uncertainty d squared plus t minus x all things squared. Okay, so here this percentage uncertainty in this one is given by uncertainty in this one. Uncertainty in d squared plus t minus x all things squared over the value of it, d squared plus t minus x all things squared into 100%. Okay, so I need to find, I'm just writing it, I'm going to erase it. So uncertainty in d squared plus t minus x all things squared. Do we know that? Yes, we know that. We already found it in the previous part. We showed it almost equal to 0.11, right? So I know the uncertainty of d squared plus t minus x all things squared. We found it in the previous part. That is the third part. We showed it 0.11, but actual value is 0.106, is it? So I'll find that value here. So by substituting uncertainty in this value, that is 0.106 over I need to find the value of this one. So d squared, 5.10 squared, 5.10 squared plus t minus x. So if I find the t minus x, you can find it from here, t minus x. Uh, t minus x, you will get 0.618 in centimeter. So t minus x all things squared. Okay, into 100%. That's the percentage uncertainty of this one. So again, I'm saying percentage uncertainty d squared plus t minus x all things squared is uncertainty of this value should be the numerator. We already found it in the previous part, 0.11, but actually 0.106 divided by the value of this one. So value of this one means value of d squared, 5.10 squared plus value of t minus x convert to meter, 0.618 all in square into 100% plus percentage answered in 8f into t minus x I need to find. So that is percentage, this is, you can see 8 is a number, f into this one. So this multiplying. So whenever quantities are multiplied, we know that uh, their percentage uncertainties will be added. Percentage uncertainty of x into y is equal to percentage uncertainty of x plus percentage uncertainty of y. So here 8 is a number, f is multiplied by t minus x. So that could be written as percentage uncertainty in f plus percentage uncertainty in t minus x. Okay, so we'll continue this. So I'll write this again without solving. I'm going to solve it finally. 0.106 divided by 5.10 squared plus 0.618 squared into 100% plus percentage uncertainty in f. That is uncertainty in f divided by value of f. Uncertainty in f is 0.3. So 0.3 over value of 8, 9.8 into 100 plus percentage uncertainty in t minus x. That already we found that also in second part, C part, second part, we found the percentage uncertainty in t minus x, 0.49 we got it. Now solve everything. We are getting the percentage uncertainty. So that will be 3.95 percentage. So uncertainty in N, refractive index, value of refracting is 1.54 into 3.95 over 100. So you will get it 0.06. So range of N, so I can say range of N 1.50 plus or minus 0.06. So that will be 1.48 to 1.60. Okay, now check it with the standard values. Which of these value falling within this range? 1.47 is not falling within this range. 1.52 is falling within this range. 1.66 also not falling within this range. So final conclusion, I should give the conclusion. I can say the given lens is made of crown glass. That's the conclusion. So this is the range 1.48 to 1.60. If you want, you can say the refractive index of crown glass is falling within the range of the experiment. Better say that in the right. I didn't write it, but you can better say the experimental value. The refractive index of crown glass is falling within the range of the experimental value. This given glass, the lens is made of crown glass. You can say that way. Okay, method 2, I am going to find the maximum and minimum values of refractive indexes in my experimental method. So I'm going to find the possible maximum value of refractive index, possible minimum value of refractive index, and I'm going to check whether any one of these values falling within that within the range of maximum and minimum. So there I am not going to use percentage uncertainty. I'm going to find directly the maximum value of refractive index and the minimum value of refractive index. I explained those things in my lesson. The link is given in the description part. Watch there. So here I'm going to find the n max. So I want to find the n max, maximum, the most possible value of maximum value of n according to these uncertainties. How can I find it? So I'm not going to find the percentage uncertainty here. The previous method, I found the percentage uncertainty of n, then I found the uncertainty of n, and I found the range. Here, without finding the percentage uncertainty, I'm going to find the range of n. Okay, n max I'm going to find. To get the maximum value of n, the numerator should have the maximum value. Just IGCSE symbol algebra. So the numerator value should have the maximum value and the denominator should have the minimum value. So D must have the maximum value. This bracket quantity should have the maximum value, means T should have the maximum, X should have the minimum. Same way, F should have the minimum, T should have the minimum, X should have the maximum to get the maximum N. So the maximum minimum values we are going to get by using the uncertainties, right? So I'm going to find method 2, N max. I'm going to find the possible maximum value in my experimental results. So 1 plus, so D max squared plus T max minus X minimum, all things squared over 8F minimum into T minimum minus X maximum. That's all. Simple. I'm going to find those values by using the uncertainties. Okay, so here 1 plus D max. So D max means 5.10 plus 0.01. So that is 5.11 square. So I'll directly put it. Actually 5.10 plus 0.01, 5.11 square plus T max minus X min. So that should be in meters. T max, that is 8.30 plus 0.01. So that will be 8.31. Sorry, 0.831. Sorry, 0.831 in meters. Centimeters, 0.831 in centimeters. That is the T max. X minimum 0.212 minus 0.002. That will be 0.210 all things squared divided by 8 times F minimum. So 9.8 minus 0.3. So that will be F minimum. So that will be 9.8 minus 0.3, that is 9.5 into T minimum. So that will be 0.830 minus 0.001. So that will be 0.829 centimeters minus 0. X max, add them 0.214. Okay, so solve it. You will get the N max 1.57. Same way, N minimum, that is equal to 1 plus N minimum means D minimum. To get the minimum value, numerator should be the minimum. So T minimum, X maximum, F maximum, T minimum, X maximum, right? So 1 plus D minimum squared plus T minimum minus X maximum all things squared divided by 8F maximum T minimum, T maximum, this is F maximum, yeah, T maximum minus X minimum. Okay, substitute 1 plus 5.09 squared plus 0.829 minus 0.214 all this square divided by 8 times 10.1 into 0.831 minus 0.210. Carefully check it. Yeah. So you will get minimum value. That means I put the denominator maximum values. As you can say, this is maximum compared to this one. This is the maximum. This is the minimum, right? So you'll get 1.52. That means the range of n here, range of n, I'm going to get 1.52 to 1.57. That's the range. 1.52 to 1.57 is the range. So which of these quantities or which of these refractive index are falling here? This is not falling within this range. This is falling. This is also not falling. So in this method, whatever the method you follow, the final conclusion will not change. It will be the same. So in this second method also, if you follow this method, here also, the range, the refractive index of crown glass is falling within the range of my experimental value. You have to give the conclusion. I'm not writing. You should write it. So the refractive index of the crown glass is falling within the experimental range. Therefore, the given lens is made of crown glass. Okay. This way also you can do. So here also crown glass. That's the conclusion you have to see. Made of crown glass, is it? Because the reason that value is falling within this range. Okay, third method, same question, third method, another method also I'll tell. So there we are going to find the percentage differences between my experimental value and the given values. One by one, I should find the percentage differences. I need to find the percentage uncertainty same way as I found in method 1. So I'm not doing it again. You know how to do it because go through it again. The method 1, I found the percentage uncertainty in N. So I'm not doing it here again. I already did it. So I'll write that one. So percentage uncertainty in N, we found it in the first part. Method 1, method 1, I found the percentage uncertainty, that is 3.95% we got it. Okay, you know how to find it. You can watch again the method 1. So that's the way we have to do, but you have to work it out. If you are following this method, you have to work it out and find the percentage uncertainty. Then without finding the uncertainty, method 1 we found the percentage uncertainty of n, then we found the uncertainty n, and we found the range, is it? So here this method, you find the percentage uncertainty in n. I'm not going to find the uncertainty. I'm going to find the percentage difference between my experimental value and for each of them. So I can say for Pyrex, percentage difference equal difference over. So 1.54 minus 1.47 over, this is the standard value. So we should divide by them into 100. So you will get that percentage difference will be 4.76. That is greater than percentage uncertainty, which is 3.95. So in my lesson, I told that if you want to accept a value, the percentage difference must be smaller than the percentage uncertainty. So here, the percentage difference between my experimental value and the refractive index of Python is 4.76, which is greater than percentage uncertainty, which is 3.95. Therefore, it is not 5x. So I can say not 5x. Okay, we'll check for crown glass. Percentage difference will be 1.54 minus 1.52 over 1.52 into 100%. So that will be, you will get 1.3 percentage, which is less than percentage uncertainty. So could be crown glass. Okay, so if you do it for flint glass, percentage difference is equal to 1.54 is the experimental value. This is 1.66. So 1.66 minus 1.54 divided by 1.66 into 100%. That will be 7.2%, which is greater than percentage uncertainty, which is 3.9%. So that surely says not fit glass. See, this method, the third method, also giving the same answer. The lens is made of crown glass. So one of the methods you can choose to give the final conclusion. So, okay, I hope you understood this lesson. If possible, I'll discuss the other papers depending on my free time.